All right. So the plan for today's class is to start into the chapter one material. We'll see how far we get through these three sections. I would like to get at least through 1.1 and 1.2 and get a start on 1.3. We might or might not finish 1.3. The first few or couple of sections of the chapter one homework are available on WebAssign now. So 1.1 is due this coming Sunday. It's a pretty short introductory section, so it shouldn't be a big difficulty to get it done by Sunday. But mainly what my goal with section 1.1 is to make sure that you can get onto WebAssign, that you get your account created and all of that, get into the section. Remember, you have the 2-week free trial, so you have that available if financial aid hasn't come in yet, anything like that. You can log on, work through 1.1, have that done by this Sunday. And if you experience any tech issues, this is a good time to work through those before we get into a lot of the homework due dates. So yeah, so take a look at WebAssign, check out what's posted, and we'll get into the material for the class. We do have a quote of the day for today. This is from the Greek philosopher Epictetus. This is a pretty loose translation, but I think it gets at the idea of what he maybe discussed in 2 or 3 different lines. And the quote, so to speak, the loose translation is, conceit of knowledge gets in the way of learning. Or in other words, when we kind of think we know everything about a certain subject, we're unlikely to admit new information or to change our worldview on the basis of new knowledge that could come in. Interestingly, kind of for most of humanity, or recorded history anyway, we have had a problem where generating information for us to intake and build knowledge was the difficult part, right? If I wanted to know something, I had to either, go and get somebody to tell me how to do it, or maybe in, 1500, 1700 or something, maybe I could go and somehow get access to a book that was super expensive and read it in there. But in the information age, in the last maybe 30 years, 20 years or so, we almost have the opposite problem. We have so much information. We can go to Google, ask it a question, and we get 1,000 websites, all telling us slightly different versions of the answer. We have to curate information these days. We have so much information that we need to say, okay, this is good information that I'm going to rely on, and this is maybe not such great information that I'm not going to trust as truth or as valid. So how do we do that? And I think that's one of the big questions of today. And I don't think it's an easy question to answer. And I think the answer looks different for different people and for different questions. Some people try to use the cop-out, oh, we'll just listen to experts, but that just kicks the can. It's, I think, at least as difficult to define what you mean by expert. If you talk to people who say, just listen to the experts, and you dig into what do you mean by expert, it usually turns into one of two things. It's either, well, the people who say the things that I agree with are who I call the experts, and the people who disagree with me are the goofballs. Or it turns into, well, if they have this credential or that credential, then I define them as an expert. And you say, well, what about this person who has that credential who you think is a goofball? And they say, oh, well, I mean, that doesn't count in that case, right? So it turns into a no true Scotsman fallacy, where we're just arbitrarily deciding whether this person or that person's an expert. So I think that's one of the big questions of today is, how do we curate information? We have tons of information. How do we find reliable information? Okay, so moving on to the chapter one material. So chapter one, we're starting with the very basics. I know that most of you all kind of know this material. This is going to be review, but we're also kind of establishing a structure. So we're going to start working with some basic ideas. We're going to define a certain number system, how it works. So for instance, whole numbers and natural numbers. We're going to define some operations and look at how those operations apply to that number system. The four operations we're typically going to look at are addition, subtraction, multiplication, division. And then we're going to look at maybe some applications, some way to model these different number systems. So we're starting with the whole numbers just because that's kind of the natural place to start. And then we'll build up to things like, say, integers, build up to fractions, ratios, percents, decimals, things like that. And at the end of the course, we might even touch on a little bit of algebra, a little bit of solving equations. So that's kind of the goal. Again, the goal of chapter 1 isn't to teach you these operations on whole numbers for the first time ever. I know this is review, but it's really to kind of establish this structure. And I think by the time we get to, say, fractions and adding, subtracting, multiplying, dividing fractions, we'll be up to a point where it's going to be fairly challenging, and there will be some real dusting off of cobwebs and so on. Okay, so let's start with the question of what are the whole numbers or the natural numbers? So the natural numbers are sometimes also called the counting numbers. And these are the numbers that we would use to count things. So numbers like 1, 2, 3, 4, and so on. When I write an ellipsis, these 3 dots, that just means, and kind of keep going in this fashion, keep the pattern going. So 5, 6, 7, 8, and so on forever. The natural numbers are infinitely long. 1,000 is a natural number, 100 million is a natural number. So these are the natural numbers. The whole numbers look a lot like the natural numbers. So the whole numbers include all of the natural numbers, but also 0. And one way that I kind of remember the difference is whole, W-H-O-L-E. It's a homonym with H-O-L-E, and 0 looks like a hole, right? Like a hole in a piece of paper or something. So 0, the whole, is part of the whole numbers, and the natural numbers are the ones that are more natural to start counting things. If you have a shelf with apples, you start counting them 1, 2, 3, 4, 5. You don't start counting with 0 usually. Now you might say, why don't we just talk about the whole numbers? Well, 0 is actually a really important idea, and we're so used to it today that we take it for granted, but there was a lot of time in history where people didn't think of 0 as being a number, right? It's kind of like there's nothing there. How do you count something when there's nothing there? So this 0 is actually a non-trivial abstraction from the natural numbers to say that there's this 0 element. And actually the 0 element is quite important when we're doing arithmetic manipulations or algebra, or even just understanding the structure of how all of this works. So we'll talk about the additive identity a little bit later, and 0 is this thing we call the additive identity. It serves an incredibly important purpose. So we have natural numbers and whole numbers. Now be a little bit careful. You've probably also heard of the integers. We are jumping a little bit ahead here talking about integers, but I want to make sure that we understand what we're not discussing in chapter 1. The integers include all of the whole numbers. So they include like 1, 2, 3, and so on, as well as 0, but also all of the negatives of the whole numbers. At this point, we're not discussing integers. We'll move to the integers a little bit later, but we're leaving that to later. But I just want to be clear about that at this point, we're only talking about positive whole numbers, 1, 2, 3, 4 being the natural numbers, or the whole numbers, the positive whole numbers plus 0. So, so that's the scope of chapter 1. We're looking at natural numbers and whole numbers, operations on them, and applications of them. As I mentioned already, we have 4 basic operations that we're going to be looking at in the context of a bunch of different number systems: the whole or natural numbers, the integers, the fractions, decimals and percents, real numbers. So we're going to introduce a new number system, look at these operations, look at applications, and then move on to a different number system that generalizes, that expands that idea, and look at how these operations work, look at the applications of that next number system. That's really kind of the structure of this course. So I think the most natural place to start with the natural numbers is with money, with currency. So if we think, I'm not a great artist, so I'm just going to draw dollar bills like this with a box with a 1 in it. So imagine that's a dollar bill. If I have another dollar bill next to it, collectively, I would say that I have $2. If I have a few more dollar bills, well, maybe I don't want to carry around all of these 5 $1 bills. That's kind of annoying to keep track of. I can kind of lump them all together, take them into a bank, and they will give me a $5 bill in exchange for them. So I can group 5 $1 bills together into a single $5 bill. That's sometimes more convenient to carry around. Or maybe I could group, if I had a collection of 10 $1 bills, I could take them into the bank and I could exchange this collection of 10 $1 bills. I could think of it as 2 groups of 5. The bank would give me 2 $5 bills. That's one option that I could have. I could have 2 groups of 5. Or they would also be happy to give me a single $10 bill. I could group them together even more to make a single $10 bill. Right? Kind of similarly, if I had 20 $1 bills, I could group these as, say, 4 $5 bills. I could think of these 20 $1 bills, which I'll just write as kind of 20 circles over here because circles are a lot quicker for me to draw. Each one of these groups of 5, I could convert to a single $5 bill. I could get 4 $5 bills. Or I could block them off slightly differently. I could look at these top 2 lines where I can see there are 10 $1 bills. These little circles again represent $1 bills. I could choose to exchange that first 10 for a $10 bill and the same for the second 10. I suppose I could even do, say, a 10 and 2 5s if I wanted to. I could group them that way. Or I could go as far as to look at the whole block and exchange these 20 $1 bills or the 4 5s or the 2 10s for a single $20 bill. I could do something similar with, say, 50 ones and a $50 bill, or 100 ones and a $100 bill. So this is, I think, a good model for the natural numbers. we kind of intuitively understand how all of this works. We've worked with money a whole lot, and money is an important part of our everyday life. And uh, we do have a little bit of a downside here, though. This grouping is kind of, in some sense, a little bit silly. Why do we have currency that's like 1, 5, 10, 20, 50, 100? Well, I mean, these just tend to be convenient denominations, convenient amounts of money for us to use in trade, right? I mean, we have $2 bills, but we just like basically never use them. They do exist. You could probably go to the bank and, exchange two $1 bills for a $2 bill and give it to your kid, and they'll be all excited because they have a $2 bill and none of their friends do. So we have other, you know, units of currency, but they don't get used. Why don't we have a $6 bill? Well, because a $6 bill is close enough to a $5 bill that it doesn't make sense to have a different one, um, based on just how often it would be used or how useful it would be. So we have these different denominations that basically are just there for convenience of trade. Can we come up with maybe a better structure to represent natural numbers that maybe is going to work a little better with how we want to do mathematics? Right? A structure like this, there's not too much mathematical rhyme or reason to it. It's more about just the utility in trade for these different denominations. Well, if we want to, we could work off of what we call a base 10 system. Instead of thinking of my currency, so to speak, being denominated this way, I could have, like, so to speak, $1 bills, $10 bills. I could exchange 10 $1 bills for a single $10 bill, $100 bills, $1,000 bills, and so on. So I could exchange 10 $10 bills for one $100 bill, or 10 $100 bills for a $1,000 bill. This isn't the way that our US currency works, but it could work that way if we had decided to set it up that way. So that's where this block model comes in. We're going to give names to these things. We're going to say that a single block, we call this thing a block, it represents the number one, the unit, a single entity, or the start of the natural numbers. If I collect 10 of those blocks together, I can kind of glue them all together and make a rod that represents the unit 10. It represents kind of, if you took 10 individual apples, you smush them together and put them all in a bag. Now you have a bag of 10 apples. You have kind of like one entity that represents 10 things. So the thing that we call a rod is going to represent a collection of 10. So one rod is a collection of 10 blocks. The same way that one $10 bill is kind of a representation of 10 $1 bills. Just maybe a little more convenient to carry around a $10 bill. It might be a little more convenient to talk about a single rod of size 10 rather than 10 individual blocks. We can add another layer. We can look at a square where I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 blocks left to right. So for instance, this top layer here, this top layer represents one rod. The layer below that represents a second rod and a third. So if we layer 10 rods together and kind of glue them all together, we get one square that represents 100. This one square, this 100, consists of 100 single blocks all glued together, or it consists of 10 rods glued together. So sometimes if I have a bunch of rods floating around, it'll be better for me to glue them together and make one square that's easier for me to talk about or to move around or to manipulate than having a whole bunch of these different rods. So let's look at this example and say what natural number is represented by this block model. Well, how many blocks, rods, and squares do I have? Well, I see that I have one block. Here are my rods. I see I have 1, 2, 3, 4, 5, 6. By the way, OneNote loves to correct my 4s into 9s. And of course, I won't do it now. But you can see with my 4 here, it kind of connected that line across the top. So um, I'll try to be clear whether I'm writing a 4 or a 9, but sometimes OneNote tries to be more helpful than it needs to be. But I have these rods. I have 6 rods. And then I have 1, 2, 3, 4, 5 squares. So I have kind of one unit, one block that doesn't have enough counterparts to glue together to make a rod. I have 6 rods that doesn't have enough counterparts to glue together to make a square. And I have 5 squares. This represents the number 561. Because remember, squares represent hundreds, rods represent tens, and blocks represent ones. So this represents 561. There are actually 561 little tiny squares, little tiny blocks in this picture here. I wouldn't want to draw this out by hand. That's why I screen capped it from our book. Can we draw a block model representation of the number 257? Let's go the other direction. So 257, well, I have 2 hundreds, 5 tens, and 7 ones. In other words, I have 2 squares, 5 rods, and 7 blocks. So I have my 2 squares, which I'm going to draw somewhat abstract. This way, I'm not going to draw all 9 lines up and 9 lines across for each of them. I have 5 tens, 5 rods. Again, I'm just going to kind of suggest the division of the rods, not draw all the lines out. So I have 2 squares, 5 rods, and 7 blocks. There's 3, there's 6, and 1 more makes 7. So this would be a block model representation of 257 of that number. So something that we've already kind of used, we haven't explicitly talked about it, is place values. Right? 2 squares or 2 hundreds, 5 rods, 5 tens, 7 blocks, 7 ones. So the number 257 is different than the number 527 or 572. It's different than the number 2570. So the idea of place values is very important. So if we look at these first 3 here, the ones, the tens, the hundreds, we know that the ones correspond to blocks, the tens to rods, the hundreds to squares. When we have something like this, we call it a period. So this grouping of three numbers, we call a period, where we have the square, rod, block construction. So I have, and for this number, I have 4 ones, 4 blocks, 9 tens, 9 rods, 100, 1 square. So just these last three numbers would be 194. And that will be our number. We could represent it with, again, 1 square, 9 rods, 4 blocks. If I have a bigger number, so if I have a number like 194, that's what it would look like. If I have a bigger number like 278,194, after I go past the first period, if I need more numbers, I put a comma in. This comma separates the periods, and it makes it easier to read the number. If I just had a string of 6 numbers, it makes it really hard for me to see, like, wait, is that 5 numbers or 6 numbers? But with the comma, I can tell really quickly what periods I'm dealing with. So if I jump over to the next 3 numbers, 278, I actually notice something here. Let me use my highlighter. In my first period, the middle increment is tens. And in my second period, the middle increment has to do with tens. In the first period, my leftmost increment has to do with hundreds. In the second period, it also has to do with hundreds. And in my first period, my rightmost is kind of ones, and in the second periods, it's thousands. That is, maybe I'll go back to my highlighter. That is what, maybe this would be a good color to use. That is the name of that period. The ones period or the thousands period, for instance. So something like 278, this would be another period. If I were to say that each block represents 1,000, then this would be like 8 blocks, where now each block in the second period represents 1,000 instead of just 1 unit, just 1. The 7 would represent 7 rods or 7 10,000s. And the 2 would represent 2 squares or 2 100,000s. So in the second period, block equals 1,000. In the first period, block just was equal to 1. We have another period, say the millions, where now a single block equals 1,000,000. And again, we have the same structure, that the rightmost digit gets the name of the period. The middle digit in the period is related to tens. And keep my color scheme the same here, the leftmost digit in that period is represented or is related to hundreds. So, and I can put commas between these. So for this number, I notice that I have 2 periods, the thousands period and the ones period. I would verbalize this as 278, which is that number, 278,000, because it's in the thousands period, 194. Or a number like 5, 278, 194, which is kind of modeled here, I see that I have a third period added on. I have a number in the millions period. I have some in the thousands and some in the ones period. So I would say, what is this number? 5,278,194. So again, I mean, I know that we're familiar with how to say these numbers and so on, but we're really examining the structure underlying all of this. This is going to be super helpful when we start talking about things like decimals, right? Maybe we're not quite as familiar with how decimals work or numbers to the right of the decimal point. It's going to build right off of this model. So that's why we're going through this, right? It's not that, I think that you don't know this or that you've never seen it before, but it's that when we get to harder things, we're going to see that those harder things are really just natural extensions of the models that underlie these easier things. So I know that you know how to say these numbers, but you might have never really thought of it in terms of this idea of periods and this consistency between the different hundreds and the tens and the ones and so on, or the way that this can translate into a kind of a block rod square model that kind of is in a sense related to how our currency works. So tying some of these ideas together into kind of a cohesive framework is going to help us for some of the more challenging material later in the course that might not be so obvious. So we're really laying out the framework here. Yeah, great. Elaine says, I was never thought to think of place values this way. It's very interesting. To be completely honest, I wasn't either until I started teaching these courses. I hadn't thought of it this way either. So yeah. So I think this is actually very valuable. And I mean, I made it through grad school in math and never thought of place values this way until I started teaching. And I thought, oh wow, this actually like makes a lot more sense than than the way I was introduced to it. So I actually found this valuable and knew when I learned it, for my job teaching this material. Um, so I'm glad that you guys that you're finding it interesting. Okay, so along with, let's see, can I shrink this down just a little bit? Along with the help of this table, let's look at this number, 78320,465. Let's look at a couple of the numbers and name their place values. So first, let's look at the 8. So I note that the 8 is in the first, second, it's in the third period. It's in the millions period. So it's going to have something to do with millions. And within that period, it's the rightmost number. It's the first number kind of counting from the right to the left in the millions period. Since it's the first number in that period, it just gets the name of the period. In other words, millions. Or in the millions period, we would think of this as being like 8 blocks, where each block represents a million. For our number 4, we see it here. We note that it's in the first period. It's in the ones period. But within that period, it's in the leftmost place. It's in the place corresponding to hundreds of ones, or for that, we just say hundreds. For 2, well, 2 we see is in the second period. There's the first period, that 465. The 2 is in the second period, and it's the middle number in that period. So it's in the second period, the one corresponding to thousands, and it's the second number, the middle number in that period, the one corresponding to 10 of those things. The middle number always corresponds to 10 of whatever you're talking about. And in this case, the period is thousand, so it's the 10,000s. And similarly, the 6, it's in the first period, middle place. The first period is the ones period, the middle place is the tens. And for the ones period, we just say ones, tens, or hundreds. We don't append anything to the end of those. So we just say it's in the tens place. And then finally, the 7, it's in the first, second, third period. And it's the second number from the right. So in the third period, we are in the millions period, not the first, but the second number from the right. That always corresponds to the tens of whatever we're talking about. This is 10 millions. And if we wanted to verbalize this number, we would go through, we'd say, okay, 78 is in the millions period. So we'd say 78,320,465. Any questions so far? All right, so let's look at rounding. So to round a whole number to a specific place value, we have a couple of steps here. First thing we do is we locate the given place value, the place value that we want to round to. And any digit strictly to the left of that place, that does not change. We keep those digits the same. And there is a little bit of a special case here, but at least in the basic cases, we kind of keep those the same. The second thing we do is we look at the digit 1 to the right of the place value we're interested in. We actually don't care about any of the other digits further to the right, just the one digit to the right of the place we're interested in. And then we ask, is this digit greater than or equal to 5? If it is at least 5, 5, 6, 7, 8, 9, then we add 1 to the digit in the place value. If it's 9, then we have to, things cascade a little bit, so that's a bit of a special case. If not, if that digit is not greater than or equal to 5, if it's 0, 1, 2, 3, or 4, then we leave that digit in the place value alone. And then we replace all digits to the right with 0. So let's look at these 3 examples. So we want to round each of these numbers to the nearest 10. So what's the first thing I do? I locate the given place value. This is the tens place value, that 5. I look 1 digit to the right. That's the number 4. Since 4 is not greater than or equal to 5, I, as we would say, round down. I keep the 5 the same. The numbers to the left stay the same, again, except in that kind of special case. And then the 4 becomes a 0, and any other numbers to the right would also become zeros. We don't have any other numbers to the right, so 354 rounded to the nearest 10 is 350. If we look at 1,427, we have a similar operation. We're still rounding to the nearest 10. So I locate the tens place. That's the 2 in this example. I look 1 number to the right. That's the number 7. The number 7 is indeed greater than or equal to 5. So I add 1 to the digit in the place value. The 2 becomes a 3. The digits to the left stay the same. And everything to the right of the place value of concern, everything to the right of the 2, turns into a 0. 1,427 becomes 1,430 when rounded to the nearest 10. And similarly, 285, still rounding to the nearest 10. So 8 is in the tens place. One digit to the right, that is a 5. Is this greater than or equal to 5? Is it 5, 6, 7, 8, 9? Yes, it is. So I round up, as we say. My 8 becomes a 9. I add 1 to that digit. The numbers to the left stay the same. And the numbers to the right all become zeros. So 285 rounds up to 290. So let's look at these two examples, rounding these two numbers to the nearest thousand. 1,832, 1,489. So I'm interested in the thousands place. That's this place here with the 1. I look one digit to the right, and that's an 8. Is that bigger than or equal to 5? Is it 5, 6, 7, 8, or 9? Yes, it is. So I add 1 to it, it becomes a 9. The numbers to the left all stay the same. The numbers to the right all turn into, oh, I jumbled up my places, didn't I? Was just checking to see if you were paying attention. My number 8 is bigger than 5, so my 1 becomes a 2. My numbers to the left all stay the same, but I don't have any numbers to the left, so nothing to concern myself with there. And the numbers to the right all turn into zeros. So 1,832 rounds up to 2,000 when rounding to the nearest thousand. For 1,489, again, rounding to the nearest thousand, we locate our thousands place. That's the 1 here as well. We go one digit to the right. That's a 4. Is this digit bigger than or equal to 5? Is it 5, 6, 7, 8, 9? No, it's not. So I'm going to round down. My 1 stays the same. Any numbers to the left stay the same. There's no numbers to the left, so I leave it as is. And then the other numbers to the right all become zeros. Now I do want to look at one special case. Sometimes when we have 9s floating around, that kind of messes things up a little bit. So I see that, for instance, 265 would round up to 270 when rounding to the nearest 10. 275 would round to 280. 285 would round to 290. 295, that should round to 300, right? I mean, that seems to be the pattern. So if I look at, say, 295, rounding to the nearest 10, I locate my tens place. That's where the 9 is. Go 1 to the right. Is that digit greater than or equal to 5? Is it 5, 6, 7, 8, or 9? Yes, it is. So I add 1 to the 9. But like, when I add 1 to the 9, do I do something like this? Like turn the 9 into a 10? Well, this doesn't work with our number system, right? Let's rewind a little bit. Let's go back up to our block model. So if I have, say, 9 rods, if I have a collection of 9 rods, okay, I have these 9 rods, that's fine. If I tack another one on by, say, incrementing a number up by 1, say when I'm rounding, if that results in me having 10 rods, it's a little silly for me to talk about this as 10 rods. That seems pretty cumbersome. I would glue that together and make one block. Or if I had 9 blocks and then I tacked another one on, I would glue those together and make one rod. If I have 9 of a given place value, and then I want to tack another one onto that, that just makes one more of the next place value over. This is that whole carry the one that everybody kind of remembers. This is why we carry that one. 9, say, rods plus one more rod. Well, we wouldn't want to call that 10 rods. That's just overly cumbersome. We just call it one block. We just move one place value over and increment that by 1. And notice that that actually kind of works pretty well, right? Our 2 just kind of combines with that 1 from the 10 in a sense. So we wouldn't write this as like 2, 10, 0, not only because that's a confusing notation, but also because it's more sensible to say, okay, increment this 9, but the 9 goes up and becomes a 10, which puts a 0 in the tens place and takes our 2. We had 2 squares before and 9 rods. When we round, we get 2 squares and 10 rods, but that's really just 3 squares. And then everything to the right becomes 0. Right, so this squares and rods and blocks model, it is, I think, pretty helpful. So, similarly, if I had, say, let's say 19,731, and I want to round to the nearest 1,000. Here's my 1,000. Number to the right is 7. I want to increment my 1,000, my 9, by 1. I don't want my 9 to go to like a 10 again, because I now have, in the thousands period, I have 9 blocks, and then I'm sticking another block onto that. I might as well glue those together and make an additional rod. I had 1 rod there already. I might as well just deal with 2 rods instead of 1 rod plus 10 individual blocks. So my 9 increments up to 0, kind of like wraps around almost like a clock face. My number of rods, my second digit in that period, increments by 1. I previously had 1 rod, 9 blocks. I got another block from the rounding. 1 rod and 10 blocks. Those 10 blocks glue together to just make 2 rods. And then everything to the right just zeroes out. One little side note, I do like to point out mistakes that folks often make, just so that you can be aware of them and make sure not to make those mistakes. Some folks would look at something like this and they would say, okay, 1,489, and they would start with the rightmost digit. They would say, okay, 9 is bigger than 5, so I round up. So kind of like in an intermediate step, they get like 1,480, or sorry, 1,490. And then they'd say, okay, 9 is bigger than 5, so I round up, and they would do something like 1,500. And then they would say, okay, 5 is bigger than or equal to 5, so I round up. So then they would do like 2,000. But we see that doing that, kind of starting at the ones place and like rounding a whole bunch of times in succession, might not give us the right answer. I mean, it's also a whole lot more work, which is inefficient, but it's even worse that we might not get the right answer. This is, so when we round to a certain place, we're only really concerned with that place value and the one to the right of it. If there's other numbers further to the right, they don't really have any impact at all. And that's an important idea, right? It's an easy mistake to make, to think that maybe you need to like start at the rightmost number and kind of work your way over. And I think where this comes from is when we do, say, addition, we add two numbers together, we kind of start at the right and do the same process consecutively across all the digits. Or when we subtract or when we multiply, we do very similar operations where we kind of, in a sense, work our way consecutively right to left across all the digits, but rounding doesn't work in an analogous way to that anyway. Rounding is only concerned with the place value of interest and one place to the right of it when determining whether to round up or down. And then occasionally some of the digits to the left can occasionally change as well if we have this kind of like roll over, carry the one, gluing together blocks into rods or rods into squares kind of idea. Any questions on section 1.1? Okay, so let's look at an operation that we can do to the whole numbers. If we have some different whole numbers, one thing we can do with them is add them together. So again, this is kind of the structure of the course. Introduce a number system, introduce some ideas about the number system, go through the operations in that number system, add, subtract, multiply, and divide. How do they work? And then look at some applications. And usually the operations, the applications are kind of interspersed in with each other. So let's model, say, 33 plus 14 using the block model. So 33 is 3 rods. In 3 blocks. And to that, I want to add 14, which is 1 rod and 1 block. When I add together, all that I mean is take these two separate entities, kind of smush them together. So adding 3 rods and 3 blocks plus 1 rod and 1 block, essentially it's just like, just get rid of the operation and think of smushing all these together. Or in other words, I have 1, 2, 3, 4 rods and 1, 2, 3, 4 blocks. So 30, oops, I 14, so I need more blocks. For some reason I did 11, but 3 plus 4 is 7 blocks. There we go. So 33 plus 14 is 47. Now, sometimes with my block model, I get some slightly more interesting things that happen, like 25, 2 rods, and 5 blocks, plus 18, 1 rod, and 8 blocks. And I actually noticed that, say, for instance, these 5 blocks and these 5 blocks can come together to make 1 rod. So I can get rid of these 10 blocks and turn them into 1 rod. I'm left over with 3 blocks. There aren't enough more blocks to make any more rods. And if I look at my rods, I have 4 rods. That's not enough to make a square. So I now have 4 rods and 3 blocks. So 43 is my sum. If I have, say, 37 plus 68, this will take me a little bit of time to draw out, but so there's my 3 rods and 7 blocks plus 68. So there's my 6 rods and 8 blocks. Now I have a bunch of rods and a bunch of blocks. Let me start with my blocks and see if I can make any rods. So here I have 7 blocks plus 3 more. I can kind of trade these in and make 1 extra rod out of that. I have left over 5 blocks, not enough to make another rod. Now I look at my rods. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I actually have 10 rods. I can actually go ahead and glue these 10 rods together or trade them in, however you want to think about it, and make 1 square out of those. So I end up with 1 square. I have no rods left over and 5 blocks left over. So I have 1 square, 0 rods, 5 blocks. It is important that I put that 0 in there, right, and indicate that there are 0 rods, because if I just put the 1 right next to the 5, again, that the place values idea is very important. I have how many rods? 0 rods. I should say that. If I just put the 1 right next to the 5, we know that's the number 15. That's clearly not the same number as 105. Okay, so we see using this block model is pretty cumbersome, right? That's pretty error prone. It's, a little bit mind numbing to draw all of these things out and try to do this. One thing that we like to do in math is we like to abstract away. We like to say, okay, this is how something works in the real world. Can we uncover the underlying structure? And that's a little bit of about what we're doing here. We're going to look at 3 properties of addition. These are components of the underlying structure of the way that addition works. And these will apply whether we're talking about blocks or apples or oranges or cars or whatever we want to add together. The first idea that we have, so far we've pretty much only been sticking to natural numbers, 1 and above. What's this idea of 0 that's important in the whole numbers? Well, 0 is what we call the additive identity. And it has the property, if A is a whole number, A plus 0 equals 0 plus A equals A. And I know that people get nervous whenever we start putting variables, start throwing variables around or letters around in math. But what do we mean by this? I mean, I can substitute in any whole number that I want. So I could say, or maybe I should say natural number here, because this applies to whole numbers as well. But so pick a natural number, whatever your favorite natural number is. Let's say 7 is a natural number. So 7 plus 0 equals 0 plus 7 equals 7. Or if you like, 30 instead, well, 30 is a natural number. So 30 plus 0 equals 0 plus 30 equals 30. So if I take any natural number and add 0 to it, I get the same number back. Again, that seems like a pretty obvious concept maybe to us because we're so used to working with the number 0, but this is a very non-obvious thing if you haven't worked with it your whole life. What's the commutative property of addition? So to commute, if you think of like a lot of people talk about their commute to their job, it's like, you can go from your house to your job or your job to your house, going like back and forth kind of idea. So the commutative property of addition is just the statement that order of addition doesn't really matter. In other words, 2 plus 5 equals 5 plus 2. Or more generally, we could say that A plus B equals B plus A if A and B are natural numbers or whole numbers. But if I exchange the order of addition, it doesn't change the result. What's the associative property of addition? Well, we've talked about adding two numbers together. There's really no reason we couldn't add more numbers together, right? Could I add, say, 11 plus 24 plus 18? Sure, I could do that. I could just draw one rod, one block, two rods, two blocks, one rod, and 8 blocks. My blocks are getting messier. And I could count these up in 2 rods and 4 blocks. I think I'm drawing my blocks while I'm saying the other number. And so when I say 2 rods, I'm drawing blocks, I end up drawing 2 blocks. But yeah, 1 rod, 1 block, 2 rods, 4 blocks, 1 rod, 8 blocks. And again, I could say combine these 10 blocks into 1 rod. I have 3 blocks left over. I have 5 rods. So 53. I could add together 3 numbers or 4 numbers or whatever. And in the block model, it makes it very obvious that we're just kind of smushing everything together. But if I think about this addition operator, this little plus sign that we put between 2 numbers to indicate that I want to take this number and combine them in some way, that really only applies to 2 numbers. So in a sense, in an abstract sense, I need to decide which numbers to do first. Do I add 24 plus 18, get that result, and then add 11? Or do I add 11 plus 24, get that result, and then add 18? And the associative property says it doesn't matter. You can do the first 2 and then tack on the third one, or the last 2 and then tack on the first one. It doesn't really matter because kind of fundamentally what we're doing is just smushing all of these blocks, rods, and squares together and then kind of recollecting them in whatever way makes sense. So the associative property of addition says we don't need to worry about what order we do our addition. The commutative property says we can change the order of addition, and there's no concern there. And the additive identity, this 0, is the number that we can add to any number and get that same original number back. Okay, so how do we take this a step further and start adding numbers without the block model? Clearly the block model is pretty cumbersome. It's error prone. If we had bigger numbers, we're going to be writing squares and rods and blocks all day. And if we went to different periods, we have squares representing different things, and same with rods and blocks representing squares, rods, and blocks representing different things. We'd have to start using like colors or something, to differentiate them. It's going to get pretty messy pretty quickly. So it's a nice and useful way to think about addition, but we need something that is going to work better for bigger, more complicated problems, and also that's going to work better for different types of problems that we'll encounter later in the course. So what's the strategy for adding up whole numbers without using the block model? Trying to move away from that, trying to come up with a more general framework that allows us to solve more problems efficiently. Well, the first step is we take our numbers and we write them one above the other so the place values line up. So I'm going to put my ones place above my ones place, my tens above my tens, and so on. So I do 12 and 34 so that my place values line up. Typically, I'll kind of indicate that I'm adding by putting a plus over here, and I'll indicate that, or I'll distinguish my result from the things I'm adding together by putting this bar at the bottom. So I have 12 plus 34. Side note, the things we're adding together are called addends. and the result is called the sum. So you might see that terminology used somewhere. And what do? Well, we start with our blocks. We start pushing together all of our blocks. How many blocks do we have? Well, 2 plus 4 is 6 blocks. So we just add down this first column, 2 plus 4 equals 6. And then we go over and we look at our rods. I have 1 rod and then 3 more. That gives me a total of 1 plus 3 or 4 rods. 12 plus 34 equals 46, my sum. Okay, what about 37 plus 64? Well, here again, I'm going to take my 37 plus 64. I'm going to write it so that one is over top of the other and so that the place values line up. I'll indicate that I'm adding. And I'll separate my result, my sum, from the add-ins. And now I'll look at my number of blocks. I have 7 blocks and 4 more blocks. I push them together. I might be tempted to do something like this, right? 11 blocks. But then when I come over here and I do like say 9, like this certainly isn't 911. If you have $37 and you get 64 more dollars, you don't have like almost $1,000. Well, remember when we combine together more than 10 or more blocks, we can start gluing them together into rods. So 7 plus 4 is 11 blocks, but 11 blocks, that's really 1 rod and 1 block. So how many blocks do I have left over? Well, just 1. But I have 1 extra contribution to the rods now because 10 of those blocks got glued together, made another rod. So I have to account for that in the rods column. How many rods do I have? Well, I actually have 6 plus 3 is 9, plus 1 more from the one I made over here. I actually have 10 rods. Well, 10 rods, they can glue together to make 1 square. And then how many extra rods do I have left over? 0 rods. So 6 plus 3 plus 1 is 10. That's 0 rods plus, whoops, a little high there, plus 1 square. I have no other squares floating around from my original numbers. So I'm just left with that 1 square that I created from gluing together those 10 rods. And one of those rods came from gluing together 10 blocks. So this whole carry the 1 idea, that's directly related to the idea that I can glue together 10 blocks to make 1 rod or 10 rods to make 1 square. But 37 plus 64 we see would be 101. 1 square plus 1 block. What about 347 plus 25? So again, I'll write these over top of one another. And again, I have to be really careful. I don't want to just do like this because the 5 represents blocks and the 7 represents blocks. I want to make sure that I have those in the same column. The 2 represents rods, the 4 represents rods. I want those in the same column as well. I have to be careful that I line things up properly. And again, I'll put my plus sign to remind myself I'm adding and my line to separate the answer. So I have 7 blocks plus 5 blocks. Well, that's 12 blocks, or that's 2 blocks and 1 rod. How many rods do I have? 4 plus 2 plus 1 is 7. And then how many squares do I have? I don't have any extra contributions to squares. I just have the original 3 from the 347. So all of this makes 372. Now, if I add three numbers together, there's a couple ways I could think about doing it. I could break this into a smaller problem where I do say 123 plus 50. I get that answer, and then I add 250 to that. So I have 3 blocks plus 0 is 3. 5 rods plus 2 rods is 7. 1 square is 1. 173, and then I have to add 250. And I do the same thing. 3 blocks plus 0 is 3. 7 rods plus 5 rods. Well, that makes 12 rods, which is 2 rods and 1 square. And that makes 4 squares. So the total would be 423. Now note that I might realize, I might look at this, I might not, it's not a problem if I don't, I can still get the answer. But I might look at this and realize, oh, wait, 250 plus 50, that's like 2 squares and 5 rods plus 5 more rods. That just makes 3 squares. That really nicely just makes 300. Can I do that first? Can I just say 250 plus 50 is 300? I intuitively just know that. And 300 plus 123, that gives me 3 blocks, 2 rods, 4 squares. Can I do that? Can I switch the order around? Sure, because of the associative property. I can choose to add these two first and then add the 123 on it. These associative commutative properties really, make addition very flexible. If I see an easier way to do the addition, I can often take advantage of that. I saw that 250 plus 50 equals 300. I can leverage that because 300 is just a very easy number to deal with. It's much easier to deal with than, 173. Or if I get to a bigger problem like this, maybe I want to take this abstraction even further. Instead of adding two numbers together and then taking that result and adding another number on, maybe I just want to do it to all of the numbers all at once. Again, the commutative and associative properties give us a lot of flexibility in how we can approach this. So I can take 6,291. I'm writing them a little more spaced out here. I have 54,107. So the 7 is in the ones place, the 0, the 1, the 4, and then the 5 is in the 10,000s place. So it's one place further to the left from the 6. A lot of times it's good to start writing from the right side to the left because that kind of keeps everything lined up a little nicer, right? The 5 doesn't go under the 6. It turns out that the 4 is what goes under the 6. And then 2, 8, 6, 3, 5. If I want to add up 3 or even 4 or 10 numbers, the strategy is the same. I start with my blocks. Well, I start with my ones period, I suppose, in this case, because I have 2 periods here. I start with my blocks in my ones period. I have 13 blocks, which is 3 blocks and 1 rod. I have 1 rod plus 9 plus 3 is 13 rods. Well, that is 3 rods and 1 square. Now, here's something we haven't really talked about. What if I have 10 squares? What if I come all the way back up here? What if I have 10 squares? Well, 10 blocks makes 1 rod. I'll do it this way. 10 rods makes 1 square. 10 squares makes 1 block from the next up period. So I can kind of glue together 10 squares to make like 1 super block that comes from the next period up. We just keep going with this strategy. The 6, 7, 8, 9, 10 squares from the first period makes 0 squares from the first period, and 1 block from the next period up, one kind of super block. 6 plus 4 plus 8 is 18, plus 1 is 19. 19 blocks in the second period makes 9 blocks and 1 second period rod. 5 plus 2 plus 1 is 8. There are 8 second period rods. Or this is 89,033. We can put the comma back in, and that's our answer. So this model, I think, this block model really kind of helps keep things straight, I think. Okay, so let's look quickly at some applications and word problems. I know everybody tends to get a little bit scared whenever word problems come up, but word problems are actually pretty nice. Number one, they show us these very abstract concepts. How can they actually be applied in the real world? How can you actually use them to solve practical problems in your everyday life? So it gives a little bit of purpose to what we're doing. The other nice thing about them is a lot of times there's kind of a reasonability check. If I just give you some numbers to add up, you don't have any idea what the result kind of feels like it ought to be. But if I tell you, here are some things that cost this amount, you have kind of a gut feeling. You work with money and buying things all the time, so you have kind of a gut feeling what it should cost, right? If we're buying sports equipment and the bat costs $299, helmet $35, the glove $68, you're not expecting to be able to buy that all with a $100 bill, and you're not expecting it to cost $2,000. We have an intuitive idea of what the answer should be. So if I get $100 as the answer, something went wrong. If I get $2,700 as the answer, something went wrong. So translating word phrases into mathematical notation, some words that tend to indicate addition are words like plus, sum, increased by, more than, total of, or added to. And I've already kind of mentioned, but the things that we're adding together, we call those add-ins, the numbers we're adding together, and the result after we add, we call the sum. So let's look at a couple of these applications. So Aiden bought a baseball bat, helmet, and glove. The bat costs $299. The helmet costs $35, and the glove costs $68. So those are the three numbers that we're given to work with. And we're asked, what is the total cost of Aiden's sports equipment? That kind of leads us to think addition. So what do I want to do? I want to do 299. And I could write dollars for all of these, or I could just leave the dollars off and remember that my unit is dollars. Plus 35, plus 68. I need to compute this addition, and remembering that all of this is in terms of dollars. That is important, right? If I was buying a bat for $299 and I was buying a helmet off of Amazon and for some reason it was 35 euros, I can't just add different units together like that. I need to make sure everything is in the right unit first before I start adding things together. But in this case, everything is in dollars, so we are good to go. I want to add these three numbers together. And again, I start with my blocks. 9 plus 5 is 14. 14 plus 8. Well, that's what? 14 plus 4 plus 4. So that's like 18 plus 4 is 22. Sometimes that can be easier to break it down like that. 22 blocks is 2 rods and 2 blocks. I see 9 plus 3 is 12. 12 plus 6 is 18, plus 2 is 20. 20 rods makes 2 squares with 0 rods. And 2 squares plus the 2 squares that are already there gives me 4 squares. So what's the total cost? The total cost was $402. Some folks want you to like write out a whole sentence, the total cost of Aiden sports equipment was $402. You can do that if you want to, I suppose, but um, it's not a big deal for me. And certainly on WebAssign, it's not a big deal. So here's a very practical example is, you know, everything these days has the calorie count associated with it. A lot of times that they also say how much protein's in it, or, how many carbs are fat, grams of carbs are fat. Um, so what if we're kind of watching our calorie intake, or if we're trying to adjust our calorie intake to our activity level, and we go out to eat and we see that the meal that we order has these calorie counts. How many calories did we consume this meal, so that we know whether, should we have a smaller snack, or maybe forgo the ice cream tonight, or do we still have room uh, for a milkshake or whatever? Or well, I guess he has a milkshake, but do we have room for whatever else? So I want to know the total number of calories, uh, total number of calories. And again, that kind of suggests to me that I'm going to be adding some things up. So I want 420 calories plus 230 calories plus 580 calories. And again, I go down my first column, my rightmost column, 0 plus 0 plus 0 is 0. We have 0 blocks. My next column over, representing the rods, 8 plus 2 plus 3 is 13. Well, 13 rods is 3 rods and 1 square. 10 of those rods get glued together to make a square. 5 plus 4 is 9, plus 1 is 10, and then add 2 more. So that's 2 squares plus like 1 super block, right? The 10 squares, 10 of those 12 squares got glued together to make 1 block the next period up, 1,000. So our answer is 1,230 calories. Or really, if we wanted to be specific, these are actually thousands of calories. What we usually call a calorie is actually thousands of the actual thing that is a calorie. 1 calorie is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. So, any questions so far? Okay, let's look at a little bit of geometry here. We want to find the perimeter of these figures. We'll start with this one, the trapezoid. We know it's a trapezoid because it has 4 sides, and 2 of the sides are parallel to one another. So we call this a trapezoid. And to find perimeter, I pick a starting point. I pick a corner to start at, and I just walk around the figure. So I go this way. I see to go that distance, I'd have to go 24 meters. This obviously is not to scale because the 17 is longer than the 24, but I'm going to keep in mind this is all in meters. I'm not going to write meters next to everything. I have to turn and go this direction now. So I'm progressing in this direction. So I have to go 17 meters further, then 29, then 17 more, and I'm back to where I started. So if I do this kind of a thing where I walk around the loop, that makes sure that I don't miss any sides. So I need to add 24, 17, 29, and 17 all together. And what can I do? Well, I can notice that 9 plus 7 is 16, plus 4 is 20. I can remember the associative commutative properties of addition say that I can swap up the order, and that's not a problem. So 9 and 7 is 16, plus 4 is 20. That's a nice grouping to work with. And then plus 7 is 27. But again, remember 27 blocks makes 2 rods and 7 blocks. So I have 7 blocks left over, and 20 of those blocks got glued together to make two rods. Let me erase these. How many rods do I have? 2 plus 2 is 4, 5, 6, 7, 8. So 87 is my sum, my answer, and my perimeter is 87 meters. And our last example, suppose we won't start 1.3, but we'll kick that to Tuesday's class meeting. So let's start here on the top left, and again, go around our figure. So we have 25 inches plus 10 inches plus 14 plus 7 plus 11. And we might make a mistake here. We might just, if I just looked at the numbers and added them up, I'd stop here and I probably would think I would get the right answer, but it wouldn't be the right answer. I see that very clearly as I'm walking around and being careful to catch all of the sides. This side, I'm actually not sure what its distance is. Can I figure it out from any of the other distances? Well, I have a little bit of a hint here. I noticed that this line all the way across the top is 25 inches long. And if I kind of put together the two lines, the two horizontal lines that make up kind of the bottom, they add to 25. I would think that the same thing would work for the sides, right? If the total height of the figure is 10 inches, I can see that here. If this distance is 7 inches, it feels like this distance should be 3 inches. So we actually needed to do a little bit of problem solving and just kind of use some creativity to figure out all of the inputs. We have this extra 3 inches that we need to add to the end, and that does bring us all the way back to where we started. So this idea of like walking around the figure, even just with your pen, it is quite helpful. Make sure we didn't miss anything. So we need to add together 25, 10, 14, 7. Let's make sure the digits, the ones place is under the ones place. That looks good. 11 and 3. Again, with the 3, make sure that it's under the ones place and not accidentally under the tens place or something. So what can I do now? Well, I have a lot of ones places to add up, but I can notice that like 7 plus 3 makes a 10. And I can notice that 5 plus 4 plus 1 makes another 10. Grouping into tens like this can often be helpful. 7 plus 3 makes a first 10. 5 plus 4 plus 1 makes a second 10. So that's a total of 20 blocks. That is 0 blocks with 2 rods. And then 2 plus 2 is 4, 5, 6, 7. So I think my total perimeter is 70. And what are my units? Everything is in inches. So my perimeter is 70 inches. Okay, any questions on anything from 1.1 or 1.2? Again, we'll kick 1.3 back to Tuesday's class meeting. But any questions on anything we covered today?
Yeah, can you go back to the one you just left?
Yeah.
How did you get the 3? I missed that. The 3 inches?
Oh, yeah. So I realized that the total height of the figure, whether I'm on the right side or the left side or the middle, the total height has to be 10 inches because of this measurement. And the total height is also made up by these two left edges, right? The total height on the right edge is all just kind of one edge, but the total height on the left edge, the left boundary, consists of those two edges here. One of them is 7 inches, and one of them is the thing I don't know. So I know that 7 plus question mark equals 10. That's got to be a 3. So that putting that 3 inches in there is what makes up that height on the left side to make 7 plus 3 is 10 inches. So it matches the 10 inches on the right. Yeah, great question though. And to be fair, we're kind of working our way into subtraction here. So this is kind of introducing the idea of subtraction of whole numbers, so it's kind of a segue into the next topic. Okay, I'll stop the recording.